What cataclysmic event, what perfectly synchronized cosmic ballet would be required to dislodge not just a single colossal world, but two massive planets from their gravitational embrace of a star? And then, even more incredibly, imagine those two planetary behemoths not merely being cast out, but somehow maintaining a synchronized trajectory, heading off into the vast cosmic ocean in the exact same direction at precisely the same speed. This delicate balance would then allow them, once truly isolated in the frigid expanse of interstellar space, to gently fall into a mutual orbit, forever bound to each other. The very notion strains credulity. The odds are so astronomically slender that they border on the fantastical. Yet, in the infinite theater of the cosmos, perhaps technically possible is sometimes all it takes. And so, perhaps, it comes as less than a complete surprise that the James Webb Space Telescope, with its unparalleled vision, has just caught a living example of this utterly perplexing scenario unfolding right before our instruments in the iconic Orion Nebula. Within the sprawling, star-forming regions between glimmering celestial bodies, two planets have been found locked in a graceful dance, orbiting each other. Each of these enigmatic wanderers boasts a mass comparable to that of our solar system's own gas giant, Jupiter, leading scientists to aptly christen them Jupiter mass binary objects, or more colloquially, jumbos. One point on which the entire scientific community seems to be in resounding agreement is this: our current theoretical frameworks for the grand ballet of star and planet formation are demonstrably, unequivocally wrong. The intricate models we've meticulously constructed simply don't account for these cosmic anomalies. But in what fundamental way are they flawed? That profound question remains a tantalizing enigma, patiently awaiting its revelation. Jumbos first materialized before the astonished gaze of scientists when the James Webb Space Telescope, a marvel of modern engineering, meticulously trained its incredibly high-resolution infrared instruments upon the turbulent heart of the Orion Nebula. While it's certainly conceivable that jumbos, or similar rogue binary systems, might exist elsewhere across the galaxy, they have, until now, remained stubbornly undetected. This elusiveness is likely due to their relatively diminutive size and their utter lack of intrinsic luminosity, making them extraordinarily challenging to spot. Detecting them typically requires highly specialized and serendipitous techniques, such as gravitational microlensing, which itself is a remarkably randomized and improbable method for uncovering new planetary bodies. Gravitational microlensing, that fleeting, almost ethereal phenomenon where we observe a momentary, yet distinct, amplification in a distant star's brightness, occurs because the fabric of space-time, as predicted by Einstein's theory of relativity, is warped by an intervening celestial object. This cosmic lens then bends more of the background star's light directly towards Earth. Such an event is so exquisitely rare, so contingent on perfect alignment, that none other than Albert Einstein himself initially believed we would never actually witness it occurring in nature, despite having mathematically predicted its very possibility. While our technological prowess has since advanced to an astonishing degree, enabling us to harness gravitational microlensing as a viable, albeit still unpredictable, means of identifying new planets, the fundamental requirement persists. You still need a jumbo, or any other hidden planet, to fortuitously pass directly in front of a more distant star before its gravitational signature can be discerned. Given this reliance on such an improbable cosmic lottery, it comes as little surprise that a vast number of planets have undoubtedly slipped past our observational nets, lurking unseen in the cosmic dark. We absolutely needed a telescope of unprecedented power and sensitivity, a true titan like the James Webb Space Telescope, to grant these elusive jumbos a proper, unblinking look. Yet, even when we finally pulled back the veil and discovered them, they were an absolute, unmitigated surprise, a profound shockwave rippling through the scientific community, an unexpected revelation that virtually no one had anticipated. The specific jumbos revealed by Webb's infrared eyes are, in cosmic terms, mere infants, relatively youthful at only 1 million years old. To put that into perspective, our own Earth has gracefully orbited the Sun for a venerable 4.5 billion years. But the most profoundly perplexing characteristic about these newly discovered binaries isn't their age. It's the utterly bizarre manner in which they orbit. Instead of gravitationally tethering themselves to a nearby star, or simply drifting aimlessly and solitarily through the immense emptiness of space, like most other rogue planets we've previously cataloged, these jumbos are locked in an intimate, mutual orbit around each other. They are true binaries, gently, almost poetically, caught in each other's gravitational embrace at an astonishingly vast distance of approximately 200 Australian dollars. That's 200 times the average separation between our Earth and the Sun, frankly. This configuration at such a scale for planetary mass objects is nothing short of baffling, challenging deeply held assumptions about how celestial bodies interact. Binary systems are certainly not an unheard-of phenomenon within the sprawling tapestry of our galaxy. In fact, they're remarkably common. Roughly 1/3 of all the stars scattered across the Milky Way exist as binary pairs or even higher-order multiple star systems, suggesting that such a synchronized configuration for orbiting bodies is quite a natural cosmic arrangement. However, a crucial trend emerges. The smaller you descend on the mass scale, the dramatically less frequently this binary configuration tends to occur. To illustrate this trend, consider the numbers. A substantial 75% of massive stars are found in binary systems. For stars with masses similar to our Sun, this figure drops to around 50%. As we shrink further to smaller, less luminous stars, the percentage dwindles to approximately 25%. And for objects smaller than a brown dwarf, those fascinating failed stars that aren't quite massive enough to ignite the sustained nuclear fusion of full-fledged stars, typically ranging from about 15 to 75 times the mass of Jupiter. A binary configuration really should never happen. Jumbos, by all established astrophysical principles, ought to be fundamentally impossible. There should be no conceivable physical mechanism or theoretical rationale for their frequency to suddenly, inexplicably leap to approximately 1 in 10. And yet, that's precisely the astonishing anomaly the JWST observed. When its penetrating gaze meticulously surveyed the vast expanse within the Orion Nebula, astronomers meticulously cataloged a staggering 540 distinct planetary mass objects, all significantly smaller than typical brown dwarfs. And of these hundreds of solitary wanderers, an astounding 9% were found to be gracefully orbiting each other in binary pairs. To twist the knife of probability even further, 2 of these objects were even discovered circling each other in a triplet system, a phenomenon that truly defies the already slender odds. 9% is an absolutely astonishing, almost defiant, number at this incredibly low mass scale. As soon as scientists fully grasped the sheer prevalence of jumbos, realizing just how common they were within the Orion Nebula, they immediately recognized the profound implication. Our long-held models for planet formation simply could not be correct. The existing frameworks are incapable of explaining this cosmic abundance, primarily because there are only 2 main, albeit flawed, explanations for the potential origin of jumbos, and neither of them offers a perfectly satisfactory solution. The nascent stages of any planetary system are invariably a period of immense chaos and violent upheaval. You've likely encountered vivid artistic renditions depicting a molten, scorching young Earth, incessantly bombarded by a relentless rain of comets, asteroids, and other space debris. This primordial debris was far more abundant in the solar system's infancy, where microscopic dust grains gradually coalesced into pebbles, then rocks, then mighty asteroids, and eventually, through gravitational accretion, colossal planets with enough gravity to sweep up everything in their vicinity, inevitably triggering a cascade of cataclysmic collisions along the way. Sometimes, however, that powerful gravitational pull didn't result in 2 objects smashing directly into each other in a fiery crescendo. Instead, under just the right set of circumstances, it could violently fling them out of their nascent orbital pathways, sending them careening uncontrollably into the desolate, frigid abyss of deep interstellar space. This dramatic ejection can even befall truly massive planets if the gravitational interactions are sufficiently potent and precisely timed. For instance, some esteemed researchers postulate that our own solar system once harbored an additional gas giant, an unruly behemoth that was ultimately bullied and ejected by the superior gravitational might of Jupiter, or possibly Saturn, though the prevailing consensus tends to favor Jupiter as the celestial brawler. Jupiter's immense gravity, like a cosmic slingshot, repeatedly tugged and perturbed the orbit of this unfortunate gas giant until it was inexorably sent spiraling outward, forever exiled into the vast, lonely stretches of interstellar space. The concept of a single planet, even one as gargantuan as Jupiter, being forcefully ejected into the boundless void of interstellar space is not, in itself, considered particularly extraordinary or rare. Indeed, it's widely believed that countless wandering, rogue planets of all conceivable sizes are fairly commonplace throughout the galaxy. There could be billions, perhaps even trillions, of these solitary vagabonds silently drifting between star systems in our Milky Way, potentially implying that there might be a greater number of free-floating planets than those securely bound in orbit around stars. But the sheer numerical abundance of rogue planets alone simply cannot account for that astonishing 9% binary ratio observed among jumbos. Therefore, something fundamentally different, something far more complex, must be actively at play. The alternative leading explanation, that these planets somehow form directly from collapsing gas clouds in the sparse, cold environment of interstellar space, much like miniature stars, unfortunately doesn't hold up under scrutiny either. While full-fledged stars can indeed coalesce and ignite in this manner, often triggered in the chaotic aftermath of a supernova or through powerful solar winds pushing matter outward, an object on the much smaller scale of a planet shouldn't possess the inherent capability to form in such an isolated, self-contained fashion. This limitation is largely imposed by something known as the opacity limit, which effectively sets a lower threshold on the minimum size of objects that can spontaneously form from collapsing gas clouds without the gravitational assistance or influence of a parent star. Essentially, gas clouds either possess enough mass and density to collapse into at least a brown dwarf, the smallest type of failed star, or they completely resist collapsing, remaining diffuse and dispersed. Here's why this crucial limit exists. When a cloud of gas begins to coalesce and contract due to its own self-gravity, it inherently loses gravitational potential energy. This lost energy must then be radiated away into space as heat to allow the collapse to continue. However, as more and more gas gathers together, the cloud progressively becomes denser and more opaque. This increasing opacity acts like a thermal blanket, effectively trapping the generated heat inside. This process generates an immense internal pressure, acting as a formidable invisible shield, pushing back vehemently against any further gravitational collapse. While nascent stars, drawing upon the immense, chaotic energies within their turbulent nebular birthplaces, manage to muster the additional force needed to punch through this oppressive barrier and continue their arduous journey to ignition, planet-sized objects find themselves in a far more precarious situation. Lacking the sheer monumental mass of their stellar counterparts, or any comparable external infusion of energy, they simply cannot generate the requisite oomph to overcome this critical threshold, effectively halting their formation through direct collapse. Is it an insurmountable obstacle for these smaller, less energetic aggregations of matter? Consequently, scientists are now actively scrutinizing the cosmic recipe, searching for that elusive, additional ingredient, a previously overlooked factor, perhaps a subtle tweak in our understanding of celestial mechanics, that could elegantly explain the startling genesis of a jumbo, not within the familiar cradles of stellar nurseries, but adrift in the vast, unforgiving expanse of open space. Personally, I find this particular line of reasoning far more appealing, imbuing the phenomenon with a compelling sense of cosmic order and inherent logic. Imagine for a moment, if a mechanism exists, however subtle or profound, to bypass or circumvent this formidable opacity limit, then these colossal, planet-sized objects wouldn't be cosmic anomalies, but rather a natural, perhaps even inevitable, byproduct spontaneously coalescing from the ubiquitous tapestry of interstellar gas and dust. Envisioning two such majestic, newly formed Jupiter-mass behemoths, born in relative proximity, gently spiraling inwards, drawn by their mutual gravitational embrace, to settle into eternal, stable orbits around each other. A celestial waltz performed in the absence of any parent star paints a truly captivating picture, doesn't it? This elegant scenario, crucially, sidesteps the astronomically improbable odds inherent in the rival ejected planet pool table collision hypothesis, a theory that relies on a series of incredibly precise, chaotic gravitational interactions akin to billiard balls caroming perfectly in the cosmic void, where planets are violently flung from their stellar systems and then, against all statistical likelihood, somehow meet and bind together. Furthermore, this opens up a tantalizing possibility. If Jupiter-mass binaries can form this way, why not smaller pairings? We could be talking about binary planets, perhaps even Earth mass or less, silently executing the same intricate celestial ballets, their existence currently veiled from our most powerful observatories, including the magnificent James Webb Space Telescope, simply because they are too faint, too distant, too agonizingly tiny for even its unparalleled vision to discern. Yet, what if the answer isn't a brand new revelation, but rather a forgotten whisper from the past, an old theory waiting for its moment to shine? Cast your mind back to 2001, a time when the very concept of jumbos, rogue planetary giants roaming unbound, was still far beyond the wildest imaginings of most astronomers. It was then that the esteemed researcher Alan P. Boss published a provocative paper proposing a fascinating mechanism. Objects slightly smaller than Jupiter, he suggested, could indeed coalesce directly from the diffuse tapestry of interstellar matter, provided that exceptionally strong magnetic fields were intensely active during this nascent formation process. These potent magnetic fields, acting almost like a cosmic slingshot or a gravitational escape hatch, could theoretically impart a sudden, powerful expulsion to the newly formed planet-mass object, wrenching it free from a larger, collapsing cloud, a cloud that, left undisturbed, would inevitably continue its gravitational descent to become a brown dwarf or even a star. In this dramatic scenario, the nascent planet is preserved and flung out into the void, perfectly intact, while the remaining, much larger portion of the cloud proceeds to collapse, fulfilling its destiny as a stellar remnant. Boss's groundbreaking paper, in true scientific spirit, candidly acknowledged its speculative nature, admitting that it was largely conjecture and emphasized that significantly more theoretical and observational work was undeniably needed to validate its audacious claims. However, what makes this old theory so remarkably compelling today is its startling prescience. The predicted mass range for these magnetically ejected objects uncannily aligns with the very sizes of the jumbos we are now observing. This wasn't a retrospective fit. These predictions were laid out clearly, years, even a full generation, before the first actual sightings of these enigmatic wanderers. Could it be that the blueprints for these cosmic anomalies were pinned long before we ever knew to look for them? So, does magnetism truly hold the elusive key to unlocking the enigmatic secret of Jumbo's existence? At this nascent stage of discovery, with so many questions still swirling in the cosmic dust, it is undeniably far too premature to make such a definitive pronouncement. What we can confidently assert, however, is a profound and perhaps humbling realization. Our previously held understanding of the cosmos, particularly regarding planetary and stellar formation, was far less complete, far more fragile, than we had ever dared to imagine. It's as if a fundamental piece of the celestial puzzle has suddenly appeared, forcing us to reevaluate the entire picture. The sheer, undeniable existence of jumbos, these free-floating planetary behemoths, doesn't merely tweak our theories. It fundamentally calls into question almost everything we thought we had meticulously pieced together about the elegant, intricate processes by which stars ignite and planets coalesce from the cosmic ether. It starkly reveals glaring gaps in our understanding, unequivocally demonstrating that more rigorous, focused, and imaginative research is not merely beneficial, but absolutely desperately needed to reconcile these new observations with our established frameworks. But isn't that, ultimately, where the true thrill and profound joy of scientific inquiry lies? This isn't a setback. It's an exhilarating invitation to delve deeper, to challenge assumptions, and to expand the very boundaries of human knowledge. Indeed, while having a robust, well-established theory provides a crucial scaffolding for our understanding, acting as a mental roadmap through the vast wilderness of the unknown, the moment we encounter an anomaly, that unexpected observation that jarringly breaks the very foundations of that elegant construct, should never be perceived as a failure. On the contrary, such a revelation is precisely where the most profound advancements often spring forth. It's not a defeat, it's a thrilling, invigorating discovery, a cosmic aha moment that shatters old preconceptions and, more importantly, presents an unparalleled opportunity to tear down antiquated walls of thought and erect in their place a far more nuanced, richly detailed, and ultimately truer understanding of the intricate tapestry of reality itself. So, in essence, what are these mysterious jumbos? They are, quite simply, strange, enigmatic entities, colossal objects, each possessing a mass roughly equivalent to our own solar system's king, Jupiter, yet found performing an isolated, delicate, and often perplexing cosmic ballet through the vast emptiness of space, entirely without the gravitational anchor of a star to call home. True celestial nomads. But beyond their immediate, captivating strangeness, these unbound giants might just be far more than mere astronomical curiosities. They could, in fact, represent the crucial, long-sought Rosetta Stone, the pivotal piece of the puzzle that finally, irrevocably unlocks the deepest secrets of how stars and planets, in all their glorious diversity, actually come into being across the universe. Their existence forces us to confront the very foundations of cosmogony, pushing us towards a more complete and coherent picture of our cosmic origins.